Okay, I think we are live, and this is the seminar of the National Observatory, the Center of Astronomy. So first of all, I would like to thank the audience for attending this seminar despite the Event Horizon Telescope announcement. I'm sure this is related to the importance of our speaker, so it's a pleasure to introduce Eleonora di Valentino. She did her PhD at the University of Rome, postdocs in Paris, in Manchester, in Durham, and now she's a research fellow at the University of Sheffield. Eleonora has been one of the most active researchers on tensions of the standard cosmological model, and she will give us an overview on these cosmological tensions. So Eleonora, thank you very much for accepting the invitation, and you can start your seminar.
Thanks a lot. Thank you so much for inviting me and for the wonderful introduction. Okay, so let me start with the famous aphorism, all the models are wrong, but some are useful, because this is particularly appropriate for our Lambda Cold Dark Matter model, the standard model we use in cosmology, because even if these can provide a fit of the available cosmological data, is based on three completely unknown quantities. And these in particular are an early stage of accelerated expansion, the inflation, which produces the initial time density perturbation needed for such a formation, a clustering matter component to facilitate the such a formation, the dark matter, and an energy component to explain the current stage of accelerated expansion, the dark energy. And between all the possibilities, we are choosing the simple guesses for this Lambda Cold Dark Matter model. So the inflation is given by a single minimally coupled Rorolli scalar field. The dark matter is a pressureless fluid made of cold and collisionless particles, and the dark energy is a cosmological constant term. So this 6-parameter approach lacks the deep underpinning some model requires to approach fundamental physics law. It seems more an approximation to an underlying physical theory that has yet to be discovered. For this reason, the deviations that we see now between the different values, the key parameters obtained for the different observables can actually indicate tension, can actually indicate deviation from this model and a failure of this Lambda Cold Dark Matter model. So the current cosmological tensions and anomalies are the topic of the review paper we submitted for the SNOMAS call that has been co-authored by more than 200 people, and is based on the letter of interest we submitted in August 2020. These are perspectives for the next decades, the Hubble constant tension, F sigma 8 and S8, and the age of the universe in this curvature. But actually there are many other less discussed, less standard existing signals in cosmological astrophysical data that are in tension with the Lambda Cold Dark Matter model. In many cases, these are controversial, so there is currently debate in the literature if this could be due to possible systematics. I encourage you to have a look at the paper if you're interested in learning more. Today, I just focus on the Hubble constant tension, the S8 tension, and the curvature. So the H0 tension has now reached the 5 sigma disagreement, and this is the most statistically significant and long-lasting tension between the value obtained by the Planck collaboration, a CMB experiment, assuming the Lambda Cold Dark Matter cosmological model, and the value directly measured by the SCHUTZ collaboration, calibrated the supernovae with the C phase. This measurement here is based on a distance ladder. What does it mean? H0 is measured via 3-step or 3-rung distance ladder. So we are calibrating the here the C fates are calibrated using a geometrical argument, so like parallaxes, masers, or detached eclipsing binaries. Then these C fates calibrated in this way are used to calibrate the type 1a supernovae in the nearby galaxies, and then these type 1a supernovae are used to obtain the Hubble flow. So we have their distances and their recessional velocity, and we can obtain the Hubble flow. So in this way, what the SHOES collaboration has done has been to use a chi-square statistics to fit at the same time all the three steps of this ladder, and in this way has obtained the very strong constraint on the Hubble constant value. On the other side, we have instead the CMB constraints. How are these obtained? So we have an early measurement, and in this case, a measurement of the recombination. And then we have to assume a model from an expansion history that describes the expansion history from the recombination to us. And assuming this expansion history, then we can estimate the Hubble constant at this expansion rate today. So the CMB, everybody knows that it is a black body spectrum, and we have a small anisotropies on this black body, and we can expand the Legendre polynomial, the two-point correlation function between the difference of temperature and the direction in the sky, and we can extract, for example, the temperature power spectrum in this way. But now then we have to assume a model which uses a set of cosmological parameters that can describe our model, and we vary these parameters, and we see that we have similar effects for different quantities. This is because they are correlated one with each other. So we choose a set of cosmological parameters, we compute our theoretical model, then we compare the model with the data, and using a Bayesian approach, we can constrain the parameters. So from a CMB experiments, we can extract for independent angular power spectra. We have the cross correlation of the temperature. We have the autocorrelation of temperature, cross correlation between temperature and polarization type E, autocorrelation, polarization type E and type B. So we have 4 independent CMB observables, and if we are looking at the constraints we obtain for these different observables, we see that they overlap one with each other. So these are the 2D contour plots. On the x-axis, we have the independent parameters of the Lambda Cold Dark Matter model. On the y-axis, we have the derived parameters. So since they overlap one with each other, this means that the different observables of Planck are in agreement, and we can combine all of them together. So this will be the constraints on the parameters of the standard model obtained by Planck. So we see, for example, that we have several indications for of sigma for the cold dark matter density. We have the scalar spectral index that is almost 1, but not exactly 1 for the dynamics of the inflaton field. So the Planck constraints are a wonderful confirmation of a flat Lambda Cold Dark Matter model, but they are model dependent. So this means that if we change the model at the beginning and we analyze this Planck data with a different models, the constraints can be completely different. The second point, we have the degeneracy between the parameters that we have to take into account because they can bias the final results. So now we have these 2 measurements, one are in early time and one are late time. They disagree at 5 sigma. So we have to ask if there are any other H0 estimates that can help us solving this puzzle. Yes, these are the other CMB experiments, ground-based telescope like SPT3G or ART.release4. Both of them are in agreement with a lower value for H0, in agreement with Planck. But we have also other early time measurements like the baryon acoustic oscillations that if combined with the BBN, so this combination is CMB independent, we see that it's still in agreement with Planck, and this is still Lambda Cold Dark Matter dependent. So on one side, we have the early universe measurements On the other side, we can find the late universe measurements, and we see that, okay, this vertical orange band is the value obtained by Shoes, this vertical pink band is the value obtained by Planck. You can make your own plot using this tool on GitHub. Here we have many measurements that have error bars so large to be in agreement with everything. So let's take a filtered plot with only the high precision measurement of the Hubble constant. So we keep here just the measurements with error bars less than 1.5 km per second per megaparsec, and here less than 3 km per second per megaparsec. And we can see that we have a high consistency at both ends of this plot. So a solution to this Hubble constant problem should have enough rigor to explain all of these multiple observations. So now let's look better at the late universe measurements. So we have the supernovae calibrated with the C-fates, and these are the Shoes measurements. Then we can have the supernovae calibrated with the tip of the red giant branch, and this is the peak of brightness reached by the red giant stars after they stop using hydrogen and begin fusing helium in their core. Here too we see that many of these measurements have error bars really big, so we can look just at the most strong constraints, and we see the famous and well discussed Friedman and Friedman et al. Measurements, because they are completely in the middle. So they are in agreement within 1.5 sigma with both with Planck and with the Shoes measurements. And now there is the new reanalysis by Anand et al. Of the same data, and we see that this is shift more in agreement with the Shoes results. Then we have the surface brightness fluctuations. Here, these are different. The Keaton et al. Result is using the SBF to calibrate the supernovae, while the Blakesley et al. Results is using the SBF as the longer indicator, and this is calibrated with both the C-fates and the tip of the red giant branch, and is very important because the two different calibrations, they are completely in agreement one with each other. They give exactly the same value. So in this case, we don't see the difference we see when these two C-fates and TRGB are used to calibrate the supernovae. Then we have the supernovae, type 2 supernovae. Then the Megamass Cosmology project, and in this case there is not a distance ladder, but this is using just directly the Hubble flow. Then the Tully-Fisher relationship, again this is calibrated with both C-fates and tip of the red giant branch. And finally there are the strong lensing measurements, and these measurements, okay, the previous one were much more in agreement with Shoes because they were assuming specific lens mass profile that was a power law. Now if this assumption is relaxed, we see that we have very larger error bars. This is TD Cosmo and the plus minus 5 or 6. And once we combine this with SLACS, that is another sample, we see that shift more in agreement with Planck. But again, these results are really also in agreement with Shoes. They are really model dependent, not only Astrofísica, but also Lambda Cold Dark Matter dependent. So now what we can try to do is, following the method used in this paper, to combine all of them together. Of course, they are correlated, so we have to be careful in doing this combination. And all of them together, the tension is well above 6 sigma between these late time universe measurements and Planck. We can try to do a jackknife of the results, remove one group of measurements at a time and taking the one with the largest error bar. And this is obtained when we remove the Shoes measurements, of course, but still, if we average all of these measurements, the tension is above 5 sigma. And we can do the same removing two groups of measurements. So, and in this case, this is obtained when we remove the Shoes results and also the strong lensing results, and we see that the tension is still at about 4.8 sigma. So it's really robust. And has been noticed by Friedminer paper here that in the last 40 years, it seems that the Hubble constant measurements are actually converging to the same value, but what is missing here is an indication of what has been measured by what. So the important point now is that there are no direct measurements that are below the indirect ones, vice versa. You see here, all of the late time measurements are giving a larger Hubble constant value than the early measurements. So if we have some kind of systematics, we should expect a scatter around the true value, and this is not happening. So a single type, single systematic error is not enough, seems not to be enough, because even if we remove some group of the measurements, the tension is still there. Multiple related systematics error are less likely because, okay, these systematics should bias all the late time, some group of. And so another possibility is trying to change the model that we use to derive the indirect constraints. So first of all, we can consider the three pillars. So consider modifications in the dark matter sector. And in this case, the most classical extension is varying the effective number of relativistic degrees of freedom. This is considered an early solutions because it's actually modifying the expansion history before a combination. And we are here playing with a strong correlation there is between the Hubble constant and the neutrino effective number. So if we want to be in agreement, we choose following the direction of the correlation between these two parameters. We need each an effective around 4. And this is completely ruled out by Planck at many sigma. And actually, when we vary the neutrino effective number, the tension is still there. So it doesn't really go away. So an early solutions like that doesn't seem really to solve the tension. So we can try to consider modification in the dark energy sector. In this case, a classical extension is to consider variation of the equation of state of the dark energy. This is considered a late time modification of the expansion history, where we are replacing the cosmological constant with the dark energy with an equation of state free to vary. And this can completely resolve the Hubble constant within 2 sigma with all the problems that a phantom dark energy from a theoretical point of view has. Okay, but we can always think about a model that behaves effectively as a phantom dark energy, but doesn't have all of these problems. So if we now want to classify the formally successful models that can solve H0, and we just take the Planck data, we change the model, and we analyze this Planck data, we derive the constraints on the Hubble constant, we compare then this value with the Hubble constant measured by shoes, okay, without any consideration about model comparison, chi-square, goodness of the fit. We see that the excellent models that can solve the tension are actually or late time modification of the expansion history. Let's see an example. We have a Farker vacuum metamorphosis. This is a phase transition in the natural vacuum. This is motivated by quantum gravitational effects, so can mimic a phantom dark energy behavior over redshifts, but is a first principles theory. So in this case, we have that the expansion behavior is different above and below the phase transition. Above the phase transition, we have matter plus radiation plus curvature plus a constant, while after the phase transition, we have something that redshifts rapidly away like radiation. So the original Parker vacuum metamorphosis doesn't have any constant high redshifts, so we can put this equal 0. And we have this relationship between the massive scalar field and the matter density. So this kind of model doesn't have any additional degrees of freedom, but has exactly the same degrees of freedom as the Lambda Cold Dark Matter model. So we use this model to fit the cosmological data, a combination of CMB, Planck, BAO data, and Pantheon that are supernovae data. gives H naught exactly 74 as expected and completely in agreement with the choose value. But the point is that for the same number of degrees of freedom of the Lambda Cold Dark Matter model, this is worsening the chi-square of about 96. So this means that this model fails to recover the shape of HZ at low redshift. Why this is happening? Because a combination of BO and supernovae data is giving a constraint on this green region here that is the product between the Hubble constant and the sound horizon. So if we want to be in agreement with a larger value for H naught, we need the sound horizon, a much lower sound horizon, while if we want to be in agreement with shoes, we need a larger value for the sound horizon. So a solution that is a late time solution moves along this line of correlation. This means that can increase H naught without problems, but can't actually move at all the sound horizon. So all the late time measurements will be completely in disagreement with BO data. So in order to be in agreement with all the data we have available, we need something that moves along this line of correlation that can lower the sound horizon and increase H naught at the same time. And to do that, we need something that is an early time modification of the expansion history. So we saw the neutrino effect in number. Another possibility is an early dark energy, that is an ejection of energy before a combination. But actually, what is interesting is that all of these models are centered around the Lambda Cold Dark Matter model. So the alleviation of the tension we see is not because there is a better overlap, but because it is a volume effect to do the larger error parts. And also, if we consider this early dark energy model actually, and we don't use a prior on the Hubble constant, we see that the tension is still above 3 sigma. So now if we want to classify the formally successful models that can solve H naught considering a combination of data sets, we see that we have many more early modification of the expansion history, early solutions. Again, this is not taking into account model comparison and a chi-square analysis. So now, why formally? Because we have to be careful that the choose collaboration is not measuring H naught, but the supernovae absolute magnitude MB. And then using the Hubble flow of the supernovae in this redshift range is obtained H naught. And using also a cosmography like this, that means some information that is beyond the local universe. The effect is negligible, but it is again, is in any case an information that is not local. So if we want if we use this example of an hotkeys stick, the energy equation of state that has a transition very low redshifts, something like that can completely resolve the Hubble constant tension, but is in disagreement with the value of the absolute magnitude MB at more than 5 sigma. Because we are not taking into account the magnitude redshift. We are losing information about the magnitude redshift relation of the supernovae. So if we want really to combine our model with the shoes measurement, instead of using an H naught prior, what we should do is use an MB prior. And in this way, if we then combine with Pantheon, we are not double counting the supernovae in this redshift range. We don't lose the information of the magnitude redshift relation. And even if we look at the MB tension, this is still at about 3.4 sigma. So now if we want to classify the successful model that can solve the MB tension, and this has been done in the Olympics paper, we see that just 3 can actually alleviate the tension below 3 sigma, and between these, just 1, a closed universe with a varying electron mass, can also improve the fit of the data. Okay, so the fact that a late time universe modification couldn't really fit the magnitude redshift relation of the supernovae is another argument used against the late time solutions. But let's see another example. We have an interaction between dark matter and dark energy, not gravitational. So we are modifying the conservation equations through this interaction rate that will be proportional to the dark energy density and the conformable rate via this dimensionless parameter xi that is negative to avoid early time instabilities. So if we assume a model like this, we see that H0 is completely in agreement with shoes. And again, this agreement is due to a better overlap between the value obtained using Planck and the shoes value. Why we have this better overlap? Because in this kind of model, we have a flux of energy from dark matter to dark energy. And since the CMB is measuring accurately well this product here, with the peak structure in the damping tail, if we have less dark matter, we need to have a larger value for the Hubble constant, naturally. And this actually is confirmed by the fact that we have just an upper limit for the cold dark matter density in this model. What happens when we add a prior on the Hubble constant? We can do this because they are completely in agreement. We have more than 5 sigma indication for a coupling different from 0. Now we want to do a model comparison using a Bayesian evidence that is based on the Occam's razor principle. So additional parameters, models with additional parameters are penalized if they don't improve significantly the fit. We can use the bias factor, that is the ratio of the likely probabilities. So this, if this value is larger than 1, 2.5 or 5, we're in presence of weak, moderate or strong evidence for model 0 against model 1. If we do that for our interacting dark energy model, we see that from Planck alone, we have a weak evidence for an interacting dark energy. And from Planck plus prior on shoes, the Hubble constant from shoes, the evidence is actually strong. But what is the problem here? The problem is that if we simulate an experiment like Planck, assuming a fiducial model with no interaction between dark matter and dark energy, and then we analyze this data letting this additional parameter xi free to vary, we have a fake detection for an interacting dark energy, a more than 99% confidence level. And this is due to the degeneracy between the parameters. So the posterior of xi is skewed towards negative values because of the correlation with the other parameters. So in order to break this degeneracy, we need to add an additional data set that is, in this case, is BAO. So we have just a lower limit for the xi parameter, perfectly in agreement with the fiducial value we used. So now what happens when we use the real BAO data and we add this to the real Planck data? We have still an indication for xi different from 0, but just 1 sigma, so not statistically significant. And we have a much larger value for H0, alleviating the tension with shoes at 2.1 sigma. Unfortunately, this indication doesn't survive when we consider the full shape power spectrum of the BOSS data list 12 galaxies. These are have additional information, are the Fourier counterpart of the BO data, but have the additional information for the pre-reconstruction data. And we see that in this case, we have just a lower limit for xi, and H0 shifts again towards a lower value. But here we have to be careful with the interpretation, because the BAO data are formed here at the combination, so they and we are measuring them here in the near universe. So in many points of the data reduction process, we have to assume a model to extract this data, and the model that is assumed is always the Lambda Cold Dark Matter model. So for models that differ consistently from the Lambda Cold Dark Matter model in the with the perturbations in the nonlinear scales, it's not clear if these data sets can be used as they are, or if they have to be revised completely when applied to extended and exotic dark energy cosmologies. So these residual tension that we see, or this between the BO and FS data and shoes, could be still a statistical fluctuation because we need to reconsider these data sets from the beginning, or can be still a disagreement. In this case, this kind of models should be ruled out completely. Okay, at the moment we don't have, we can't really say this because this BAO and FS data have been tested for, and they are completely reliable for early time modification of the expansion history, but for late time modification that falls within the parameterization W0, WA, the CPL parameterization. So for all the others model, we really don't know. We have to be careful when we rule out all the models, the late time solutions, because they are in disagreement with the BAO data. So now what about the MB tension? Okay, if we see this tension, okay, we consider a combination of Pantheon, BO, and BBN, this is 2.4 sigma, so it's still alleviated. And then if we use an MB prior, we see that again, we can solve the tension with a coupling different from 0 and more than 2 sigma. So now in this kind of models using a prior on H0 and MB is exactly the same, and they can also fit the magnetoredshift relation of the supernovae, and that's because this is a smooth modification of the expansion history. So the problem we saw before using an H0 or an MB prior is really true just if we have strange modifications and the Hubble law is no more valid, but for smooth modification this is valid and doesn't make really any difference. Now let's see another example. We can Taylor expand the dark energy density around a possible extrema at a scale factor AM. So this will be the expansion rate, and this will be the dark energy equation of state. And if we analyze the cosmological data, assuming this phantom crossing model, we see that we have a phantom crossing of more than 2 sigma. When the CMB is combined with all the other data sets, and H0 has a larger value, alleviating the tension with shoes at 2 sigma. What is important here is that actually this model can also fit better the BAO data, better than the Lambda Cold Dark Matter model. And if we look at the chi-square for this kind of model, these are improved for all the data sets. So this phantom crossing is a late time modification of the expansion history, but still works in solving the tension, still can give a better fit of the data because this is allowing for negative dark energy. So just to say that there are many possibilities that have been proposed. They work, but they don't work really well. They are in disagreement most of the time with something else. So if we look at the proposed model, okay, the proposed model are at least 300, but these are 180 are the models for which we can put a point on this plot. In order to be in agreement with all the data sets we have, we need a point that is in agreement with this cross here and this cross here, and this is not happening at the moment for any of the models we have. So at the moment there is no case for a model being better than all the others. So we don't have still a solution to the Hubble constant tension. But let's see an additional complication. This is that when we try to alleviate the Hubble constant tension, we are at the same time increasing the S8 tension. S8 is defined as a combination of the clustering parameter and the matter density. And this is a parameter used to quantify the tension we see in the plane sigma 8 omega matter between Planck, that is this orange region here, and CFHT lens and KITS 450 that are weak lensing experiments. If we use this S8 parameter, we see that the tension is at about 2.6 sigma, 2.5 for the Lemon alpha and a similar range of scales, 3.2 combining KITS Viking 450 and SCR1, 3.4 combining KITS Viking 450 and BOSS, that is this blue region here, we see that really far away from Planck, 3.1 for KITS 1000 alone, so it's becoming statistically significant, 2.5 for DES Y3, and actually if we overplot, that's why 3 kids 1000, we see that they are perfectly in agreement. So the different statistical significance of the tension is because they are using a different tool. For kids 1000 is more because they are just looking at S8 parameter. That's why 3 is looking at the whole volume of the parameter space. So if we do a similar plot like before, for the H0 tension, in this case S8 tension, we see that the early universe measurements, in this case, all of them are giving a larger value for S8, while of the late universe measurements with cleansing data, but also galaxy cluster counts, redshift space distortion, all of them are giving a lower value for S8. So again, the important thing that we see is a trend. So we have the late universe measurements that are giving a lower value for S8 than the early universe measurements. You can find a summary of the possible candidates that can solve this S8 tension in our review. But it's possible that actually this is due to a systematic in the Planck data, because if we consider the A-lens parameter, this A-lens parameter is introduced as like an amplitude in front of the lensing. So photons coming from recombination to us are deflected by the matter interposed. And this can be measured, this A-lens parameter can be constrained looking at the smoothing of the peaks in the damping tail. So if this is equal 1, we are in presence, this is perfectly in agreement with the general relativity. But if we measure A-lens different from 1, this could mean systematics in the experiment or new physics. And as everybody knows now, Planck is giving A-lens larger than 1 at about 3 sigma with an improvement of the chi-square of 9-10 points depending on the observable. This is not a measurement of the lensing because this can be measured by the 4-point correlation function, the lens reconstruction power spectrum, for which A-lens is exactly 1. Why this is a problem? Because if we cut the temperature power spectrum in 2 regions and we extract the parameters here, this multiple regions is similar to the WMAP1, and here we compare the constraints in this way, we see that they are in disagreement at about 2.5 sigma with the lower multiples data more in agreement with a larger value for each knot. And the way we have to solve this internal disagreement of the temperature power spectrum is fixing a lens equal 1.2, that is the best fit preferred by Planck. So we have an internal disagreement. We have this A lens that is a phenomenological parameter introduce a consistency check that is failing. And with this different from 1, we solve an internal disagreement of the Planck data. And since this is very well, very strongly correlated with the S8 parameter, if we have a larger value for a lens, we have a lower value for S8. So varying the A lens parameter, that is possible systematics in the Planck data, can actually solve also the S8 tension. So can explain completely the external disagreement of the Planck data with the weak lensing data. And this A lens parameter different from 1 is really robust because it is above 3 sigma, even if we combine with the BAO data or the Pantheon data. So now, assuming that is not a systematics, assuming that there is general relativity, is there a physical explanation for a lens? Yes, and this is a curvature of the universe different from 0 that has been measured by Planck at about 3.4 sigma, and is now confirmed by the alternative likelihood CAMP spec, for which omega k is less than 0 and 99% confidence level. So if we now look, we want to understand if this can be due to the correlation, to a bias for the correlation between the data sets. As we saw before, okay, we can have a fake detection of something because of the correlation. We can simulate an experiment like Planck, that is this blue line, assuming a flat universe, and we see that we can fully recover omega k equals 0 with a 2% uncertainty, because we can actually break the geometrical degeneracy we have in the damping tail with the matter density, using the information of the lensing we have in the damping tail. Okay, so these A result is not due to geometrical degeneracy and is statistically significant. Just with 1 more degree of freedom, we have an improvement of 11 points on the chi-square. That's because we are not only fitting better this region here, like the A length parameter, but also because we are recovering the low anisotropic quadruple of Planck. And this is in agreement with the previous findings on the WMAP temperature power spectrum, and Evsatio in this paper was actually suggesting a closed universe to be in agreement with the low quadruple of the WMAP data. So now what happens when we add the other cosmological observables? So we add the BAO data, we are perfectly in agreement again with a flat universe. So what is the problem here? The problem is that if we look at their consistency, we see this is Planck, the gray region here. These are the BAO data. They are perfectly consistent in the flat universe, but as soon as we let the curvature free to vary, these are the BAO data. You can see they are all below on the same side of the plot. And for example, these boss that are at least 12 are very far away from Planck. So they are in strong disagreement and more than 3 sigma. And this has been confirmed independently by Andre in his paper, and is true also for the full shape power spectrum, galaxy power spectrum of BOSS. So we have a strong disagreement, and in principle, we can't combine data sets that are in disagreement and believe to the result. If we now look at the lensing, we see that the best fit varying omega k is similar to the best fit varying a lens, because a closed universe means more matter means more lensing. So this is the reason why they are strongly correlated. And if we assume a flat universe, we have this strange indication for a lens different from 1 at more than 2 sigma. But a lens can be 1 if omega k is less than 0. But here we have to be careful, because a lens parameter is just a phenomenological parameter without any theoretical motivation, while omega k is a parameter of the standard model. Let's recap where this omega k is coming from. We have the essence equation that are relating the properties of the space-time, the geometrical properties of the space-time to the distribution energy of the universe. We have the Friedmann-Lemaitre-Robertson-Walker metric, where appears for the first time this curvature parameter that can be positive, null, or negative depending on the value of the curvature of the universe. So we combine them together, obtaining the Friedmann's equations that are describing the expansion history of the universe. We divide the first Friedmann equation for the critical density, that is the density we expect in a flat universe, and we have this equation for the density parameters. So if we measure omega larger than 1, omega k is less than 0, k is larger than 0, we have a closed universe. So there is no new physics here, just general relativity. So omega k is a parameter of the standard model, is not exotic physics beyond the standard model. And again, if we now cut the temperature power spectrum to multiple regions, we see that the disagreement can be perfectly solved by a closed universe, as well as was solved by a lens. And if we want to know which are the constraints on omega k by non-CMB data, combination of non-CMB data, we see that local universe, BO supernovae, BBN, are actually well in agreement with a closed universe at 60% confidence level, and well in agreement also with the Schu's measurement. The problem is again Planck, and when the curvature is free to vary, gives H0 much lower, 54 km/s per megaparsec, and is also increasing the tension in S8, the S8 tension. So actually this curvature is not solving anything, but it's just complicating the things. So this is the reason why we call this a crisis in cosmology. What about the Pantheon data? They seem to be well consistent with omega k equals 0, but if we consider an extended parameter space in which we vary at the same time also the equation of state of the dark energy, that's because we want to understand how much robust is this finding. We see that Planck is very well below omega k equals 0 and perfectly in agreement with all the values possible for H0, and actually, Planck plus Pantheon F20, that is a prior on H0 as obtained by Friedman, or a prior on H0 as obtained by Shoes, all of them are well below omega k equals 0, with the exception of the BAO data. And this is happening because all of them are ruling out the cosmological constant at more than 3 sigma. So in other words, Planck plus the luminosity distance measurements are ruling out both a flat universe and a cosmological constant more than 99% confidence level, or we have evidence for a phantom closed universe at more than 99% confidence level. Now it's difficult to understand if this model is more or less theoretically convoluted than the Lambda Cold Dark Matter model, because we are removing the fine tuning for the cosmological constant, but we are introducing the fine tuning for a closed universe. So what about the other data sets? If we look at the other CMB experiment, they are really consistent with omega k equals 0. And this is confirmed in the fact that the CMB experiment alone can actually constrain omega k without bias. But if we compare to all of them together, the CMB experiments, we see that they disagree one with each other. If we look at the single parameters, they disagree much more than 3 sigma. The overall disagreement using the suspiciousness statistics that takes into account the whole tension in the whole volume of the parameter space is 2.6 sigma. For me, this is significant because we are looking at the same observable and we are assuming the same model as the Lambda Cold Dark Matter model, and the tension is still there. So if this is true for the Lambda Cold Dark Matter model, it's still more true for the extended parameters. For example, we have that the neutrino effective number, a third neutrino is the most ruled out by at more than 2.5 sigma. We have evidence for a total neutrino mass different from 0, more than 1 sigma for ART and SPT. And actually, this evidence at 1 sigma we have from these data sets is very similar to the value we have using Planck marginalizing over this A-lens parameter. So if we assume that A-lens is a systematic, we marginalize over this A-lens parameter, we obtain a constraint for the total neutrino mass different from 0, and this is in agreement with the other CMB experiments. And if we now consider an extended model, again with 10 parameters varying at the same time, so to check for the robustness of this result, we see that the significance of the total neutrino mass different from 0 is increasing, and in this case, the H0 and the total neutrino mass are no more correlated, so we can have a prior, we can put a prior on H0, and in this case we can solve not only the Hubble constant tension but also the S8 tension with the total neutrino mass different from 0. And this is also in agreement with the BAO data. If we add the BAO data, we see that the direction of the correlation between the Hubble constant and the total neutrino mass is opposite to what we have in the Lambda Cold Dark Matter model. What does it mean? This means that if we add an H0 prior when the total neutrino mass is free to vary, we see that we have a stronger and stronger bounce on the total neutrino mass, ruling out the inverted hierarchy, but also the normal hierarchy. So they are completely in disagreement. While in this other case, where there are many parameters varying at the same time and also BAO data, we see that is happening the opposite. So we can add an H0 prior without problems. They are in agreement. So they can solve the tension with the Hubble constant and also with the BAO data, assuming a total neutrino mass different from 0. But we have other problems. We have the rounding of the spectral index and the rounding of the spectral index, and they are measured different from 0 from at 2.9 sigma and 2.7 sigma, and they are in disagreement with the value obtained by Planck, for which these two parameters are exactly 0. And again, finally, we have the famous early dark energy detection by the ACT experiments. ACT data only or combined with Planck up to multiples 650 give evidence for an early dark energy more than 3 sigma, solving completely the Hubble tension. This is still valid if we add the BAO data and the lensing of Planck. Still early dark energy more than 3 sigma, H0 slightly shift towards smaller values, but still in agreement with Shoes. Unfortunately, this evidence disappears completely, and the solution of the Hubble constant disappears completely if we use the Planck data. So again, is the damping tail of Planck to produce this disagreement between Planck and the other CMB experiments. So concluding, most of the anomalies and tensions we see are involving the CMB data. We have the Hubble-Constant tension of 5 sigma, a tension of 3 sigma, other small tension, A-length problem, omega k different from 0 from Planck, running of the spectral index or total neutrino mass from the other CMB experiments, early dark energy from ACT. So all of these tensions are presenting a serious limitation to the precision cosmology. If you want to use the CMB data like a laboratory at high energy to give some information for fundamental physics, at the moment this is not really possible. So I was sure after all of these evidences that actually the CMB results are a confirmation of a Lambda Cold Dark Matter model. In my opinion, we need more observations and alternative theoretical solution to explain all the data sets we have. Thank you so much.
Thank you very much. Very nice talk, lots of information. And let me open for questions. Does anyone want to ask questions? Actually, I have some, but I can.
I have one, Rodrigo.
Please, Gilson.
Yeah, Eleonora, very nice talk. Thanks a lot. I'd like to hear your opinion about, well, you mentioned one of the, that you call IDL models, models with interaction between dark matter and dark energy as a possible solution, right? With Q proportional to the energy density of the dark energy. As far as I understood, for this model to work properly and to solve or alleviate the H0 tension problem, C, the interactive parameter, must be negative, right? Well, there are some results showing that if C is negative, psi is negative, the energy density of the dark matter becomes negative in the future, and violating the so-called weak energy condition. So how do you see this situation for this kind of models?
Yeah, okay, so I think first of all, okay, thank you for the question. First of all, this is okay, I took this as an example, okay, to see that there are not only not all the late time solutions should be ruled out because they are in disagreement with the data sets, the bio data, because actually, okay, the bio data are not fully tested for exotic cosmologies. Second point, you are completely right. This is just a phenomenological parameterization, and actually it's difficult to find a physical explanation for all the features that this model has. And yeah, the point is exactly that the dark energy is becoming negative at the same point of the phantom crossing, you know, the other model I show you. So yes, I think that there is always a way, okay, for theorists to find a solution and avoid these problems. So I'm more data driven, so I see that there are tensions, I'm looking for possible solutions, but I agree with you, this is not the full solution, okay? I don't believe in this as the final result for solving the Hubble-Constant tension.
Yeah, and I think you're right when you say that this is pretty much the same as the phantom solution, right? It's interesting that in phantom, all the energy conditions are violated, like, for example, the energy condition. And here, in the case of the models, is the weak energy condition. So it's interesting to understand how the energy condition, the role that energy conditions play in these possible solutions of the H0 problem.
Yeah. I agree with you, but I'm also convinced, okay, that the dark energy is something that we don't know at all. So everything is possible, no? It's just something that we put by hand to explain the accelerated expansion. So there is no reason why it should be a dark energy there. Maybe it's modified gravity, maybe something else. Okay. So my point is just, okay, we had some observations. We took the Lambda Cold Dark Matter model that is this possible simple solution, and then now we are stuck with this solution. We want to see if we can I don't know, rule out this solution, but it's just something phenomenological, okay, without any theoretical motivation. So for me, everything is possible. I'm not really okay. Yeah, so I agree with you. There is a lot of work to do. There are, from a theoretical point of view, okay, none of these makes sense at all. But yeah, we need an explanation for the tensions we have now.
Okay. Thank you.
Thank you to you.
Okay, Wendert, you have a question?
Hi, thanks for the talk. I have a related question also regarding to interaction dark energy models. At some point you showed when you do simulation for CMB, even if the simulation doesn't, have any interaction, so you will find a fake interaction for the dark energy interaction. Well, I just wanted to understand this better. So you are saying your model, when you do the fitting, we will have this fake interaction detection, but when you add extra data, these will disappear. Is that right? That you were saying?
Yeah. So thank you for the question. Yes, if you look here, okay, this is the fiducial model. You see, these are the constraints that we have. So the cold dark matter density from 0.12 becomes 0.05. Okay, is almost in agreement with no dark matter at all. So that's the point, because actually, what you are measuring with the CMB are combination of parameters. Okay, so let's take an example. We have a 2D contour plots. All of the points along the line of correlation gives exactly the same chi-square, more or less. Okay, so maybe here is the best fit, but here is the true solution. Okay, and the code can't really distinguish one of the two. Okay, so for the model, for the code, having a lower value for the matter density and a larger value for H0 is exactly the same as the opposite. Okay, so this is a problem of the correlation between the parameters. That's the reason why we have to be careful when we claim that there is new physics, and we have always to check with the simulations, because it's possible that moving along a line of correlation, the best fit is in a different point of the parameter space that is not the real one. Okay.
Mm-hmm.
I don't know if this makes sense to you.
Yeah. This is, I think that this is also happening for WCDM cosmology with the CMB blank data.
Exactly.
There is a preference for phantom dark energy, but when you combine BO and others,
that's the point. If you see, when you combine the BAO data, you are measuring accurately well the matter density. Okay.
Mm-hmm.
So you fix this parameter here, and everything goes back to the normal, to the true value. Okay. So this is something you have to do. Okay, so that's the importance of combining different data sets together. But we have to be careful when we do this combination, because the data sets have to be in agreement. If we combine data sets that are not in agreement, you can find strange results. For example, you combine an H0 prior when you validate the neutrino effective number, and you claim that there is a fourth neutrino. Okay, nobody will believe to that, because they are in tension. Okay, so you have to be careful that they are in agreement when you combine them together, and they are reliable, because like BAO data, they are extracted under a Lambda Cold Dark Matter model. Okay, so in the linear regime, there could be some difference, and maybe they are not completely valid. For the simulations, you know what you are putting in, so you know the result, but this is not completely okay.
Yeah, but for this case of the BO, you mentioned that they assume a fiducial cosmology. How can you distinguish if they are in agreement? Because in the other case you mentioned, you can compute and see if the data it's in agreement if the contour lies in the same place in the parameter space. But for these, I didn't see how can I be sure if I can combine it blank with BO data or not,
Okay.
Even if they are in the same place in the parameter region, but they are assuming a cosmological model. So I'm just...
Okay, you can make an identical plot like this. I didn't do this, but you can do it. And you can see if these BAO data are in agreement with the region predicted by for your model. But that's not the point, because not only they have to be in agreement, but they also the point is that you have to be sure that they can be used for this kind of model. Okay.
I see.
so if the BAO data are assuming a Lambda Cold Dark Matter model, and what they are giving you, the collaborations, is just the value with the error bar or the covariance matrix. Okay, so in order to arrive to extract the data, you have to assume a model. Okay, so and if the model is changing and you have perturbations that are important in the linear scales, we don't know if at the end the BAO data will be the same. Okay, so these points could be in a different position. Okay, so that's the point. And they made a lot of tests. So we know the reliability in many extended cosmologies, but we don't really know for exotic cosmologies. Okay.
Yeah. If I may have a very final question. For the CMB experiment, the new ones, the ACPT and all the others ones, are they also measuring CMB lensing? If so, I would like to know if there is any lens tension in their measurement. I'm not sure if they have if they are also measuring CMB lensing. So I'm just wondering if they have, if this A lens tension also appears in other type of CMB rather than Planck.
Okay, they test the A lens parameter in the models, and this is completely in agreement with one. Okay, so there is no A lens tension. Yeah, and they have exactly the same problem like Planck. So H naught is large and H naught is lower and S8 is larger. So it's not, A lens is not the final solution for all the tensions that we have. But the fact that they disagree such a level, because A lens, Planck has this A lens omega k problem, and ART and SPT doesn't have these problems, but they have neutrino effective number, total neutrino mass in dark energy. This means that there is something there, or a systematic somewhere. Okay, this could be, or just we are not using the right model to fit the data. Okay, that's my opinion.
Okay, thanks very much.
Okay, Simone, you have a question?
No, I don't have any more because when they're stolen from me.
Sorry,
it was this question about the disagreement between the Planck CMB data and the ACT and SPT. But in fact, I would like to know a little bit more about this, because as you showed in one slide, they are considering the same model, yes, assuming the same lambda CDM, but well, they disagreement with 2.6 sigma tension. So what this is saying to us, like we should choose one experiment, and if yes, why to choose this one and not the other?
Okay, this depends on who you to ask, because Planck people is correct Planck, ACT people is correct ACT, of course. And then there are Lambda Cold Dark Matter people who think that 2.6 is not significant. People who work on tension think that this is a big tension. So, of course, this is completely subjective. But the point is that, okay, they are in disagreement 2.6 sigma. This is the whole volume of the parameter space. You see, if you look at this tension, this is above 3 point something sigma. Okay, so NS here is equal 1, so there is on the Dovich spectrum. Okay, so the point is not how much they are in disagreement, assuming the Lambda Cold Dark Matter model, but the fact that they disagree on these. Once you open to the extensions, like early dark energy, you have completely different results. So now you want to believe that the universe is closed or the universe has an early dark energy. Okay. So we are talking about this. So we have 3 sigma evidence for early dark energy from ACT, 3 sigma evidence for curvature from Planck. So which experiment do you believe more? Okay, and in my opinion, none of them, because from a ground-based telescope, you can't really measure the large scale, the low multiples data of the power spectrum, and so you don't have a full sky measurement, and you can't really remove the foregrounds, okay, because you need to the Planck results to remove the foregrounds at different frequencies. And we know that there was a claim for 7 sigma evidence for tensor to scalar ratio some years ago from BICEP, and that's because we have this problem with the lensing. They couldn't really clean the data sets without Planck. So ground-based experiments have a lot of problems. But at the same time, Planck has this A-lens problem that is a big problem, because once you look at the extended parameters that are using lensing, like omega k or like the total neutrino mass, you have strange things. So at this point, I think we need just new data. And probably it should be best to have a satellite experiment again, so you can have a better control of the foregrounds.
Okay, thank you.
Thank you.
Okay, Antonella has a question, but actually just let me say that if people from YouTube, if you want to ask a question, can write on the chat and I can read it here. So Antonella, please.
Thanks. Can you hear me?
Yes. Hello.
Yes.
Thanks, Eleonora. Very nice talk. And a lot of information about this tension in cosmology. I would like to know your opinion about the other way around, right? Because you show us many cosmological models trying to solve this tension, but maybe the tension comes from the data we are measuring locally, right? Maybe we are, I don't know, neglecting a systematic in the measure of H0, right?
Okay.
What is your opinion about that? Because I don't know, could it be possible to the origin of this tension comes from that side?
Okay, first of all, yes, of course, everything is possible. And okay, now we have more than 5 sigma, and even without shoes, we have 5 sigma. Okay, so this is what I showed before. So if we took a supernovae tip of the Reggiana branch, SBF, type 2 supernovae, Masers, and Tully-Fisher, we combine all of them, the tension is 4.8 sigma. So saying that there is a systematic somewhere without saying where, okay, is becoming a little bit odd, because or we started to think really where the systematic can be, or we have many different local experiments that are giving a larger value. Okay, this is the point. Okay, all of them give a larger value. So, and there is not a common solution. Okay, this is C-phase and supernovae, TRGB and supernovae, SBF, and this is supernovae and SBF, on SBF the TRGB, Masers, completely different stuff, lensing. Okay, so there is not a common solution for all of them. So if there is a systematics in one of the experiment, tension is still there. If there are many systematics, all of them should bias the data, the result in the same direction. Okay. And this is the point. So it seems unlikely that we have 1, 2, 3 systematics and all of them are pushing in the same direction. Okay, we should expect something above, something below, and this is not happening. And the same here for the early measurements. Okay, so this is the tricky point, I think. So systematics can be, and of course, if there are systematics, they should be in some way correlated, because we see this strange behavior of the data. But on the other side, we have the Lambda Cold Dark Matter model. We don't know anything about this. We know 4% of the Lambda Cold Dark Matter model. All of the other stuff, something that we just assumed. So, and there are no evidence from laboratory about dark matter and dark energy. So we really are, okay, yeah, we are comparing something that we don't know with something that could be. And it's difficult to say. So I just say, I'm just completely in agreement that we need new experiments, new data sets, independent way to measuring this stuff. For H0, we hope that the standard science can really tell us something, because this is a completely new way to derive the H0 parameter. And in the next 10 years, we expect to reach a 2% uncertainty in H0. So this can really help us to disentangle the problem. But at the moment, yeah, I don't see a solution, nor in the theoretical side one, in the dataset side still. Thank you.
Thanks.
Can I make Can I make a quick comment on that?
Yeah.
You said that maybe the systematics, it's very unlikely to be systematics, maybe because there isn't like they all are higher values, but I was wondering, how about the human bias systematics, you know, because one experiment finds some point higher than the other ones it tends to find the same one, because, you know, we are biased.
That's a good point, but actually all of these experiments are performed blindly. So this means that you do simulations on simulated data, and when your machinery, okay, is robust and you believe to the result, you look at the real data and you see what happens with the real data. So before there was for sure a human bias. What we don't do blindly is to analyze the CMB data. Actually, the CMB data, there is no way to have this in a blind way. So CMB data are most inclined to human errors.
Okay. Okay, I think I can now ask my questions. And at some point you mentioned this BAO data and trying to understand how to use BAO data for alternative models. And I would like to ask you, but what about these Alcock-Pazinski terms that people claim that are model independent, these parallel and orthogonal term scales that people use? I mean, I'm not a super expert, but people claim that they are model independent. It can be used for any kind of model. So how do you see that?
Okay, people claim a lot of stuff, but
yeah.
in order to be reliable, they have to make tests. And my point is just that when the data are extracted, they are assuming a Lambda Cold Dark Matter model. Lambda is a cosmological constant that doesn't have perturbations. Okay, so if we have exotic cosmologies, we have perturbations in the nonlinear scales, datasets can change. All the tests have been performed for cosmologists we know well. Okay, so the reliability of the data is for this kind of model, but for exotic cosmologists, these tests have not been performed. Okay, I'm not aware of testing interacting dark energy, for example, or modified gravity models, and see if this BAO data can be used as they are Alcock-Pazinski too. Okay, all these tests are performed always in a Lambda Cold Dark Matter model or similar. Okay, so my point is that we need to revise all of them better for particular cosmologies. This is not possible, of course, because we have 300 different models. So at the moment, this is the best we can do. So maybe, okay, if we have something really strange, for example, we know for all the early solutions, like early dark energy, this can be used without problems. Okay, the problem is with the late solution instead.
Okay, at some point in your presentation, you have shown the model with this super quick transition in the dark energy equation of state. I think it's from Valerio Marin, Davi Camarena. I mean, would you think that such a quick, I mean, when we compute perturbations and if we have a time-dependent equation of state of dark energy, probably dark energy could cluster in this kind of model. And in dark energy perturbation, there's a term that depends on the derivative of the equation of state parameter. And would you think that this kind of model could leave a kind of signal in the, I don't know, in the Paul spectrum at such a low redshifts because of this quick transition? I mean, this term that depends on the derivatives could be super high at this point and maybe leave a signal or something like that.
Yeah, okay, these kind of models have been explored by Periparopoulos and et al. Okay, all the students, Alestas and Laurentiis, and also have a paper with them about that. Yes, and the signature is expected more in the supernovae, and they claim actually that you can see this in the small different redshifts. Okay, in my opinion, this is just one of the billions model you can propose. So I don't really see this as a possible solution. Okay, this is disagreement with the value of the absolute magnitude of the supernovae. So yes, they should have a signature. People say that this signature is present in the data, but it's not statistically significant. So at the moment there is no consensus on this.
Okay, so just a very final question. It's just asking about your opinion. Recently, the DES released this 3-year result, and they claim that there's no tension anymore in S8 because they have about 2 sigma tension on S8, and that's important because now we can combine DES with Planck if we want. And I mean, this choice of there's a tension or there's not tension, it's something, I don't know, at least obscure. I mean, it's we should define something, and I mean, how do you see that, and which level of tension, in your opinion, we could say that there's no tension? Because I mean, they are super complex experiments. Of course, we will not have exactly the same result, and I don't know. So which level of tension, in your opinion, would be acceptable for combining data and making this joint analysis for cosmology?
Okay, so first of all, I'm a member of both Planck and the Kennedy survey. So and you know, okay, this is the value by kids, and this is the value by this way 3. Okay, so you see these kids 766, and this yellow 1.
Yep.
Okay, this is 759, so exactly the same. And that's
Yep.
way 2. Okay, and this is the green one, and then you do green and yellow, and you see that they are completely in agreement, one on top of each other. One collaboration claims 3.1 sigma, the other collaboration claims 2.5 sigma. Okay, how is this possible? Because the kids collaboration is just looking at S8 parameter. Okay, so they see the S8 value compared with the S8 value of Planck, and they claim 3.1 sigma. Okay, they are looking at the whole parameter space, like before, like for I show you the tension between Planck and ACT. Okay, so also the parameters that this is not actually constraining. Okay, so you have the tension in all the parameter space. So that's the reason why you have a lower tension, because you are looking at the whole volume of the parameter space, but the constraints are exactly the same. Okay, they are using different priors. So I will say, first of all, this tension is not at the level of the Hubble constant tension, because the Hubble constant tension is now 5 sigma. Okay, this is under debate because different collaboration claims different things. But again, there is an indication, like before, all of the local measurements have lower values, all of the early measurements are larger values. So something is there. Now, if this is due to a systematics in the experiment, in the CMB experiment, it can be, because if this A lens is a systematics, there is no more S8 tension, okay? Or this is a true signal. I don't know. At the moment, we can't tell this. In my opinion, okay, I will say that in between 2 and 3 is something to be investigated. We need more experiments, because between 2 and 3 is really borderline. Above 3, I will say that is significant. Below 2, probably is a statistical fluctuation. But I wouldn't say that between 2 and 3 is just a statistical fluctuation, because, you know, the first discovery of the acceleration of the universe was a 2.4, 2.8 sigma, something like that. So this is something to be investigated. Okay.
Okay, many thanks. So, Eleonora, I don't know if you have time for more questions. I mean,
yeah, I have time. So you go ahead.
Okay, so Javier, you have a question?
Okay. Thank you, Professor Eleonora. A very nice talk. I have a question about the curvature tension. So when we consider a lambda CDM model with curvature, in this context, we have a strong tension between BAO and Planck data. So in this case, it is not possible to perform a jointly statistical analysis because this high tension, and we have a problem with the lambda CDM model with curvature. But when we generalize this lambda CDM model for a WCDM or even or better, a CPL model with curvature, we have that the tension between the BAO data and Planck data is not very high. So in this case, we can perform a jointly statistical analysis, and the result of this jointly statistical analysis is very near to a curvature equal to 0 and W equal to -1. So this is not an evidence for the simple lambda CDM model. And we can continue to consider a lambda CDM model, a flat lambda CDM model, like a better model, the best model of the universe.
Okay, so thank you so much. So first of all, I'm not believing that the curvature of the universe must be positive. Okay, I don't believe the universe is closed. I don't believe the universe is flat. Okay, just look at the data. So for me, everything is possible again. Okay, so first of all, okay, in order to combine data sets together, they should be in agreement, because if we had the opposite, okay, if Planck was giving perfectly a flat universe and then combining it with the BAO, we had evidence for a closed universe, nobody would believe to that result. You agree with me? So since we have the opposite here, so Planck gives a closed universe, and when we combine with BAO, we have a flat universe, everybody believes indeed, because this is a confirmation bias. Okay. So this is the first thing, in my opinion. Second point, when you combine data sets together, it's possible that they are in tension because you have a bias when you derive a constraint. As I showed you before, for the interacting dark energy, we have Xi different from 0 because of the correlation. So this is, of course, in tension with BAO equals 0, but that's a problem of the Planck data that are giving a wrong value for Xi. So this is a tension due to your method, your statistical method you use to derive the constraints. Okay. So here we simulated an experiment with a Planck data with a flat universe. We can recover omega k perfectly 0. So this, what we see, the omega k less than 0, is not a fake detection. It's something that is really in the data. And this is the point. So you have a real indication for a closed universe in the Planck data, and you want to combine with BAO that are in agreement with a flat universe, and then you have a flat universe at the end. This is not the same when you have a phantom universe, because if you do simulations with Planck alone, W is less than -1, okay, in the simulations. So you have a fake detection for W that is not in the real data. So that's the reason why these are completely different. W is something that depends on the geometrical degeneracy. So you can have W different from -1 just because of the statistics. You can't have omega k different from 0 because you break the geometrical degeneracy with the lensing that is in the damping tail of Planck. Okay, so they are completely different. So when you do something like phantom dark energy equation of free to vary, and you add the BAO data, you are combining stuff that are in tension, but you don't really think that this is a tension because the fake detection of the phantom universe can be just a problem with Planck. If you do this with the curvature, you have a real indication of curvature, and you are combining with something that is in disagreement. So the best thing is to vary all of them together, as we did here. Okay, you vary at the same time the W, the dark energy density, and the omega k, and you see that again Planck and BO are in tension. Okay, this is here, and this is Planck. They are intentional more than 3 sigma. So again, you can't really believe to this result. Okay, I don't know if I convinced you.
Yeah, but in this case, you consider not just W different from -1, but you consider NS and
no, these are the normal data. Okay, these are the normal.
Okay, this is just the WCDM model that you consider in this case.
Okay, this is Lambda Cold Dark Matter plus total neutrino mass.
Okay, yeah.
W and curvature.
So the effect of you consider in this case neutrinos mass, it is not another effect that you can have in these results, just the more than a simple WCDM model.
Okay, this is not a WCDM model. This is WCDM plus omega k.
Well, yeah. Omega k plus WCDM plus omega k plus the neutrinos mass. So yes, this neutrinos mass is not an additional effect. It will have an additional effect than a simpler WCDM model plus curvature.
Yeah, if you go in the paper, you have all the possible combinations with many less parameters, more parameters. Yeah. They have also, I have also another paper is Anchodorco et al. Okay, and you have all this combination also including the curvature. Planck plus Pantheon, Planck alone is always preferring a phantom closed universe, whatever data set you are considering. BAO data is always in tension with Planck in this case, okay? Because BAO data preferring a flat universe. So no matter what, you have always a phantom closed universe from Planck or Planck plus Pantheon, and always a flat universe in agreement with the cosmological constant from BAO. And they disagree.
Okay.
Okay.
My comment is about because Rodrigo von Martens, Jason Ocaniza, and Mikko Benetti, we published our results about the tension between these data sets. And for example, when we consider a CPL model with curvature, we don't have a strong physical tension. So in this case, we combine all the cosmological data, and we have the result of this analysis is a preference for a lambda CDM, a flat lambda CDM model. So it's just my comment about.
Yeah, it's true, but that's because you are letting free to vary also WA, okay? So the volume of your parameter space is really the larger possible.
Yeah.
And you should check with simulations is actually having so large volume can allow you to recover the fiducial model. I don't think so, because this doesn't happen also when you vary W alone, W0. Okay, so if you have W0, WA, usually you have your posterior are moved different in a different region than the fiducial value. Okay, and your error bars are so large that they are in agreement with everything. So I agree with you. If we consider a very extended models, we are in agreement with everything, but that's just this is a volume effect. Okay, so at a certain point you have to balance which is a volume effect, so how much larger you want to go, and which is a real indication for something. So yes, I agree with you. Yeah, in that case, yes.
Okay, thank you.
Thank you.
Very nice. Thank you.
Okay, guys, I think we have no more questions. So let me thank again, Eleonora, for your seminar and for your time. I'm pretty sure we bother you too much. And
thank you so much.
Thank you again. And I will finish the seminar. So, yeah, that's it.
Thanks a lot.
Thank you, Eleonora.
Thank you, Eleonora.
Thank you.
Thank you. Bye.
Bye.
Bye.